Large language models based on transformers have revolutionized natural language processing, but their internal mechanisms remain poorly understood. A critical challenge is balancing global and context-specific knowledge. To address this, researchers have developed a synthetic dataset to study the emergence of an induction head mechanism in two-layer transformers, which enables in-context learning. Analysis of the training process reveals the role of weight matrices as associative memories, where the learning of gradients is crucial. The authors investigate data-distributional properties and the emergence of the induction head mechanism, which is essential for in-context learning. This mechanism allows the model to adapt to new contexts by inducing a context-specific representation. The researchers' findings provide novel insights into the internal workings of transformers, highlighting the importance of the induction head mechanism in balancing global and context-specific knowledge. By understanding how this mechanism develops during training, the authors aim to improve the reliability of transformers, ultimately enhancing their performance in real-world applications. The study's results have significant implications for the development of more robust and adaptable language models. By shedding light on the internal mechanisms of transformers, this research paves the way for further advancements in natural language processing and its applications. The paper introduces a new synthetic setup to study global versus in-context learning in transformer language models. It views the transformers' weight matrices as associative memories that learn to store specific pairs of embeddings, deriving a simplified, more interpretable model for the task. The study empirically investigates training dynamics with careful probing, revealing that global bigrams are learned first, followed by the formation of the induction head through learning appropriate memories in a top-down fashion. Theoretical insights on training dynamics are also provided, showing how a few top-down gradient steps on the population loss can recover the desired associative memories by finding signal in noisy inputs. This contributes to understanding internal mechanisms in transformers responsible for certain behaviors, an area known as mechanistic interpretability. In the realm of transformer models, a crucial mechanism for in-context prediction is the induction head. This mechanism consists of two attention heads, the previous token head and the induction head. The previous token head utilizes positional information to attend to the previous token, then copies its embedding. The induction head, on the other hand, uses the output from the previous token head as input and outputs the original token. This process is visually represented in Figure 1. The paper under discussion focuses on this basic copy mechanism, but it also highlights the potential for richer behaviors when combining multiple mechanisms. This could lead to more sophisticated and accurate predictions within transformer models. This paper's findings have significant implications for natural language processing and other applications where contextual understanding is paramount. By refining our understanding of the induction head mechanism, researchers can further enhance the capabilities of transformer models, ultimately leading to improved performance in tasks such as language translation, text generation, and question answering. Moreover, the exploration of combining different mechanisms opens up new avenues for research. It suggests that transformer models may be capable of even more complex and nuanced contextual understanding than previously thought. This could involve developing novel architectures or fine-tuning existing ones to better leverage the strengths of the induction head mechanism. In conclusion, the induction head mechanism in transformer models plays a pivotal role in enabling in-context prediction. The paper's emphasis on this basic copy mechanism, as well as its suggestion of combining multiple mechanisms, offers promising avenues for future research and development in the field of natural language processing. In this study, we employ a synthetic data setup to investigate the induction head mechanism in transformers. Specifically, we introduce a bigram data model with modified transitions for specific trigger tokens. By training this model on synthetic data, we achieve exceptional accuracy, exceeding 99% for fixed triggers and 95% for random triggers. Notably, attention maps in Figure 2 reveal the induction head mechanism in action, demonstrating the model's ability to actively utilize contextual information rather than relying solely on simple associations. This setup enables a nuanced exploration of how transformers learn to balance contextual cues with associations. Crucially, our results highlight the presence of a memory in the attention layer for fixed triggers, allowing the model to effectively differentiate between in-context and global predictions. Moreover, for random triggers, the model demonstrates an impressive capacity to disambiguate between these two types of predictions. This synthetic data setup provides a unique opportunity to dissect the complex interplay between context, associations, and attention in transformers, shedding light on the intricate mechanisms underlying their impressive performance. In the associative memory viewpoint of transformers, weight matrices function as associative memories, storing pairs of embeddings as a weighted sum of their outer products. To elucidate learning dynamics, a simplified transformer model is introduced, featuring fixed random embeddings. This model reveals that weight matrices indeed behave as associative memories. Notably, the gradients of the population loss take the form of an associative memory, leading to estimates of the form alpha 0 W0 plus n array summation alpha ij Wijt, where alpha 0 and alpha ij vary with the number of iterations. When W0 is a Gaussian random matrix and the dimensionality d is large, the first term in this estimate plays a minor role. The gradient updates in this scenario correspond to a maximal feature learning regime, analogous to micro-p updates in deep networks. This insight provides a novel understanding of transformer learning dynamics, highlighting the role of associative memories in the optimization process. The refined transcript for the explainer video begins here. This section of the research paper discusses the handling of superposition in transformer models, specifically focusing on a simplified two-layer transformer architecture that is more interpretable with the memory viewpoint. The authors freeze input, output, and positional embeddings throughout training, as well as certain weight matrices, to simplify the model and analyze learning dynamics both empirically and theoretically. The discussion on page 7 explores the model's capacity to balance predictions from the induction head and the feed-forward layer, particularly with fixed triggers. It emphasizes how the model tends to favor the induction head, unless its output aligns with one of the top predictions from the global bigram. This section also examines the simplified architecture, noting its limitations compared to standard transformers, but stresses its simplicity and interpretability. The empirical study section presents an analysis of learning dynamics on the bigram data, focusing on the simplified architecture. This includes the experimental setup, metrics such as memory recall probes and KL divergence, and the emergence of the induction head through top-down learning. The authors delve into the learning dynamics of induction heads in associative memory-based models, as depicted in Figure 3. This figure illustrates the results of learning the induction head alone, with some layers frozen until iteration 300. It is evident that the output matrix W20 must be learned before the key-query matrices, but it does not suffice for good accuracy. The sequence of learning W2K before W1K facilitates easier understanding, and W1K stores initial context positions much faster than late positions. Learning W20 alone resembles a bag of words model that aggregates representations throughout the sequence, which is sufficient to recover the correct associations in W20. These associations enable learning key-query matrices that focus attention on relevant tokens, eventually recovering the desired induction head behavior and leading to near-perfect accuracy. The authors also analyze the learning dynamics of the key-query matrices, finding that W2K is easier to learn when W1K is frozen compared to the reverse, yet learning them together seems beneficial due to helpful feedback loops. Additionally, W1K fits previous token associations for early positions much faster than later positions. Comparing global versus in-context learning, the authors find that when training all layers jointly, global bigram statistics tend to be learned more quickly than the induction head. The W20 probe also seems to improve quickly initially, but only leads to mild improvements to in-context predictions. The full learning of the in-context mechanism takes longer, likely due to slower dynamics of the key-query matrices. Finally, the authors examine the role of the data distribution, finding that changes to the data distribution can have a significant effect on the speed of learning the in-context mechanism. They observe that a smaller number of triggers, using only rare fixed triggers, and using random triggers instead of fixed triggers may slow down in-context learning. The authors hypothesize that these effects are due to slow learning of W20 and key-query matrices. The paper delves into the concept of associative memory in transformer models, where gradients near initialization can lead to the emergence of induction heads. It highlights that these gradients may learn associative memories that filter out irrelevant components of superpositions in inputs, focusing on useful signals instead. Theoretical insights are provided through lemmas and an illustrative example, demonstrating how data-distributional properties affect learning dynamics. In the context of a classification problem with fixed output embeddings Wu, the gradients take a specific form involving expectations and conditional expectations, allowing the associative memory to isolate relevant parts of inputs predictive of a label, leading to accurate associations. Experimental results compare global versus in-context learning and data-distributional effects, showing that training on a more diverse distribution can improve generalization accuracy without additional training cost. Additional experiments and detailed visualizations of memory associations are presented in the appendix. The development of transformers' in-context learning abilities is centered around a simplified setup to understand the model's training dynamics. Near-orthonormal embeddings are crucial, and a single gradient step is used to learn representations. The induction head mechanism can be learned via sequential gradient steps. For a deeper understanding, more complex models are required, incorporating structured embeddings, factorized matrices, and nonlinear feedforward layers. The authors present a comprehensive list of 15 distinct categories of cyber-physical system (CPS) attacks, which are classified based on the attacker's goals, tactics, and techniques. These categories include sensor manipulation, actuator manipulation, data tampering, denial of service, and unauthorized access, among others. Each category is further subdivided into specific attack scenarios, resulting in a total of 47 unique attack vectors. The authors employed a systematic literature review to identify and categorize these attack vectors, analyzing 150 research articles published between 2015 and 2022. This comprehensive review enabled the identification of knowledge gaps and areas of confusion in the existing literature, highlighting the need for a unified framework for CPS security. The proposed taxonomy is grounded in the NIST cybersecurity framework, which provides a structured approach to managing CPS risks. The authors demonstrate the applicability of their taxonomy by mapping 20 real-world CPS attack cases to the identified categories and attack vectors. This exercise reveals that the majority of attacks, 70%, involve sensor manipulation or data tampering, emphasizing the critical need for robust sensing and data validation mechanisms in CPS design. The authors acknowledge that their taxonomy is not exhaustive and that new attack vectors may emerge as CPS technologies continue to evolve. They propose that their framework be used as a foundation for future research, enabling the development of more effective CPS security solutions. This section presents a comprehensive list of methodologies and techniques employed in the research, providing an in-depth analysis of their applicability and efficacy. The study leverages cutting-edge computational tools to simulate quantum entanglement phenomena, shedding light on the intricate interplay between quantum states and environmental factors. The authors utilize advanced algorithms for data processing, ensuring precision and accuracy in the results obtained. A detailed explanation of these algorithms is provided, highlighting their role in enhancing our understanding of quantum mechanics. Furthermore, the paper discusses various experimental setups designed to test theoretical hypotheses, demonstrating the importance of interdisciplinary approaches in quantum research. It also delves into the challenges faced during these experiments, underscoring the need for further refinement of existing methodologies. The section concludes with a discussion on potential avenues for future research, emphasizing the significance of continued exploration in this field. Limitations and assumptions made throughout the study are acknowledged, adding depth and transparency to the findings presented. This research paper presents a comprehensive overview of various studies and findings in the field of transformers, in-context learning, and neural networks. It begins by discussing the impact of pre-training term frequencies on few-shot reasoning, followed by an exploration into the representational strengths and limitations of transformers. The paper also delves into the exact solutions to the nonlinear dynamics of learning in deep linear neural networks, as well as the concept that linear transformers are secretly fast-weight programmers. The authors then touch upon the idea that in-context learning can be understood as implicit Bayesian inference, and how tensor programs can be used for feature learning in infinite-width neural networks. They also discuss tuning large neural networks via zero-shot hyperparameter transfer, and the use of root-mean square layer normalization. Additionally, the paper highlights a synthetic reasoning task called LEGO, which is designed to unveil transformers. It also provides insights into the strengths and limitations of transformers, emphasizing their potential for future research in machine learning and artificial intelligence. The research discusses associative memories based on outer products of random Gaussian embeddings, building upon Section 4. The embeddings UK are considered, with I, D, Gaussian n, 0, 1, d, entries. Three key properties are recalled: norm, near orthogonality, and remapping. The norm property states that UK_TUK approximately equals 1, a standard result from the concentration of random vectors in high dimensions. The near orthogonality property states that for I does not equal j, UK_TUJ equals 0, 1, square root d, proven using the central limit theorem. The remapping property is divided into two subproperties. The first, remapping norm, states that if W is a Gaussian random matrix with I, D, n, 0, 1, d, entries, then for any fixed x, parallel Wx parallel approximately equals parallel x parallel, following the Johnson-Lindenstrauss lemma. The second, remapping near orthogonality, states that if X is a normalized Gaussian embedding and W is a random matrix, then X and Wx are nearly orthogonal, with an error bound of 0, 1, square root d, with high probability. These properties ensure correct associations in memory lookups. A precise analysis of these properties is not provided, but a more detailed study is an important direction for future work. Theoretical insights on gradient dynamics are also explored, including an illustrative example, derivations of gradients, and a study of the induction head mechanism in a simplified setup. The formulation of the attention mechanism's weights is a crucial aspect in the context of the attention layer's initialization. The weight matrix W1 is derived from the expected value of the input data. Notably, when the dimensionality is large enough, the weight matrix can be approximated as a linear combination of the input data's expected value, leading to a classifier with essentially perfect accuracy by learning to ignore spurious positional embeddings. The gradients of the attention keyquery matrices at initialization are also highlighted for their importance in forming associative memories. Specifically, the gradient of the loss with respect to the weight matrix W at zero initialization is shown to be dependent on the expected value of the input data and the softmax output. This emphasizes the significance of these initial gradients in guiding the optimization process towards desired associations. In this analysis, we examine the training dynamics of the induction head mechanism in a simplified setup, focusing on a single trigger, k equals 1, with uniform distributions over n for pi u, pi q, pi o, and pi b, I. We consider a specific loss function for sequences of length t, where the last input zt is the second occurrence of the trigger token, and the label y equals zt plus 1 is the corresponding output token. This setup can be extended to later occurrences of the trigger. When the loss is applied to all tokens and WF is learned, WF quickly learns the global bigram statistics, as observed in Section 5. The current token embedding has a strong predictive signal compared to the attention layers, initially appearing as noise. This setup is similar to that of Lemma 1, providing recovery of bigram statistics when dis is large. However, other information from attention layers in the inputs may eventually be used, biasing away from perfect recovery, as seen in Figure 4, right. To simplify the analysis, we drop the feedforward layer WF and focus on the learning of W20, W2K, and W1K in a top-down order. We consider zero initialization in a single gradient step, noting that random initialization should lead to similar associative memory behaviors when the dimension is large enough, resulting in a near orthogonal remapping of input embeddings to any output embedding. See Appendix A. We begin by studying the learning of the second output matrix W20. In the given data model, we consider a loss as in lemma 2 with input outputs, x, y, where y is the output token of the sequence. The gradient at w equals 0 includes three terms. The first term is related to the first occurrence of the trigger. The second term is related to the second occurrence of the trigger. And the third term is related to the first occurrence of the trigger with the second occurrence as the label. We then analyze the learning of W2k and W1k, providing gradients at w equals 0 for both matrices. These gradients are also composed of three terms, similar to the gradient for W20. In the realm of machine learning, a novel data model has been developed and applied within a specific framework. This model introduces the concept of a noise vector, which is composed of two components: positional embeddings and the average attention output from the first layer. The model's parameters are updated using a gradient step, with the ultimate goal of minimizing the difference between expected and actual output token distributions. Mathematical derivations play a pivotal role in this model, emphasizing the importance of residual connections and the noise vector's influence on the model's behavior. Residual connections allow for the preservation of information from previous layers, while the noise vector helps in creating a unique identity for each token in the sequence. However, the current setup has limitations, particularly in distinguishing the output token from others in the sequence. This challenge presents opportunities for future work, including the exploration of alternative methods to enhance token distinction. Such advancements could potentially improve the model's performance and accuracy in various applications. The development of this novel data model marks a significant step forward in machine learning research, offering new insights into the interplay between different components within a model. As researchers continue to refine and expand upon this framework, it is likely that further breakthroughs will be achieved, ultimately leading to more efficient and effective machine learning algorithms. The learning process for W2 is discussed, assuming it as an equation, 16. Predictions p, k, x, are essentially random for W2 with k equals 0. After one gradient step on W2 with learning rate eta, lemma 4 yields an update for W2. This update is shown in equation 17, involving expectations of w, k, phi 2 xt, xt minus x, xt conditioned on y equals k. The inputs to the second attention layer, xt, are defined in equations 18 to 20. For simplicity, only xt, 0 are used as queries and values, while only xt, 1 are used as keys. The update for W2 is then simplified to equation 21, which is further simplified to equation 22, using the fact that trigger tokens Q are sampled uniformly. Equation 23 defines at k, and the update is approximated in equation 24, using alpha equals eta per tera Newton. This approximation involves three terms: increment O, increment Q, and increment R, where increment O carries the desired signal for the induction head associative memory, and increment Q and increment R are negligible for large N. The research focuses on controlling increment OK, J, where Z2 equals Y. By expanding the expectation, the expression is rewritten as a function of a spurious positional mixture, P. The authors distinguish four cases based on the relationships between J, K, and I. In the first case, where J does not equal K and I equals J, the trigger token J appears at positions to 1 and T, resulting in ACK, J, I approximately equals gamma T, which is greater than or equal to 2, T1, for T larger than a small constant. In the second case, where J equals K and I, the two occurrences of the trigger happen one after the other, implying T equals T, and ACK, J, I approximately equals 2, T1, plus O, 1, T squared, for T larger than a small constant. In the third case, where I does not equal J and J equals K, the tokens up to position to 2 or I, D, uniform in N, J, leading to ACK, J, I approximately equals O, 1, N. In the fourth case, where I does not equal J and J does not equal K, the tokens accept at positions to 1, 2, and T are uniform in N, J, and the triggers do not contribute to ACK, J, I, resulting in ACK, J, I approximately equals O, 1, n. The authors summarized the results, obtaining 1, nnn airy summation k equals 1 ag. J. I approximately equals O, 1, n. If I does not equal j and omega. 1, t, if I equals j. This implies that when n is large and t is moderate, the sum leads to more signal in the I equals j terms compared to I does not equal j. Specifically, phi 1 we, I, 1, nnn airy summation k equals 1 increment ok. J approximately equals O, 1, n. If I does not equal j and omega. 1, t, if I equals j. Which acts precisely like the desired associative memory. The remaining task is to show that the other components are negligible compared to this, which can be achieved by demonstrating that 1, nnn airy summation k equals 1, increment qk, j plus increment rk. J, approximately equals O, 1, t. The authors focus on controlling increment q and increment r, crucial for understanding the behavior of the associative memory model. They analyze increment q, which is 0 unless k equals j, bounded by O, 1. This leads to a bound on the sum of increment q over all k, O, 1, n. Next, they control increment r using the triangle inequality and Holder inequality, providing a crude bound of less than or equal to 2 ct, n. A finer control on increment r is possible by leveraging distribution similarities. Combining these bounds, the model W2K behaves as the desired associative memory when n is large enough, satisfying equation 25. This equation indicates the model captures correct associations between tokens with a gap between correct and incorrect associations, amplifiable by increasing the step size. The authors then discuss the learning of W1K, assuming W20 and W2K have already learned correct associations. They consider a simplified architecture and analyze the update rule for W1K after one gradient step, involving a complex expression. By leveraging the fact that W20 and W2K have captured desired associations, the update rule for W1K simplifies, leading to a more tractable expression after one gradient step. The authors derive an approximation for the weight matrix W1 in the transformer model. Specifically, for any t greater than 1, W1 can be approximated as a function of the trigger token Q, the step size eta, and the scaling factors alpha and alpha. This approximation involves the expectation of several terms, including it, k, Bietti, k, quart, k, and dt, k, defined in equations 26, 29. The authors simplify these terms using the fact that the distribution of TQ is the same regardless of y. Substituting these approximations into equation 30 yields the final expression for W1, which exhibits an associative memory behavior. The weight matrix W1 is shown to be proportional to the probability of the trigger token Q appearing at position T1, multiplied by a softmax term that depends on the input sequence. This behavior matches the desired, previous token head behavior derived earlier in the paper. The authors also note that the softmax term can be saturated by choosing a large enough step size. Finally, the section concludes with a proof of lemma 1, involving the derivatives of the cross-entropy loss function for classification with k-classes. The gradient of the loss function L with respect to the weight matrix W is derived as a sum of expectations over the input and output variables. This gradient is crucial for optimizing model parameters during training. The proof involves applying the chain rule to differentiate the loss with respect to W and simplifying the expression using the definition of output probabilities and conditional expectation. In the proof of lemma 2, the gradient of the loss function is expressed in terms of the difference between estimated and true means of the input data given class labels. This highlights the role of the weight matrix in adjusting the model's predictions to better align with the true data distribution. The proof of lemma 4 focuses on the multi-head attention mechanism, where input and key matrices are denoted by x and z, respectively. The gradient of the loss function with respect to W is computed, accounting for the nonlinearity introduced by the ReLU activation function and softmax normalization. This gradient expression is essential for optimizing attention weights and improving model performance. These lemmas provide insights into computing gradients of the loss function for different neural network components, which is vital for understanding the optimization process and the model's learning dynamics. In the context of a specific neural network architecture, the mathematical derivation of a gradient calculation is presented. The softmax function of the second layer is linearized around 0, a crucial step in computing the gradient of the loss function with respect to the model's parameters. The chain rule and product rule are then applied to calculate the gradient, leveraging the previously defined linearization. The partial derivatives partial differential u, partial differential us, u equals 0 equals 1, t and partial differential us, u equals 0 equals 1, t are utilized in this process. The resulting expression for the gradient, given in equation 33, involves an expectation over the data distribution and a sum over all possible classes. Subsequent simplifications of this expression are achieved by exploiting the properties of the attention mechanism and the specific form of the attention weights. This leads to equations 34 and 35, which highlight the attention mechanism's role in computing the gradient. The paper concludes by discussing the potential extension of their simplified architecture to more complex transformer architectures commonly used in practice. These architectures typically feature additional components, multiple heads, and layers, and the authors suggest that their memory viewpoint can be applied to these models as well, providing a foundation for future work. This section delves into the factorization of matrices in transformers, concentrating on associative memory and layer normalization. The associative memory setup involves a product of matrices, which can be achieved through factorization W equals D, D, UV, where U and V are matrices with dimensions D times D and D times D, respectively. This setup is similar to an associative memory of the form W equals sigma I xi yi caret T, where xi and yi are near ortho-normal embeddings. The factorization W equals D, D, UV results in matrices U and V that are similar to those obtained from a single gradient step on U0 and V0, as shown in Lemma 1. The paper also addresses layer normalization, which is commonly used in transformers to enhance training stability. Layer normalization can be applied before or after each block, and its effect can be understood by considering the population loss L, W, equals E, X, Y, tilde operator P, L, Y, Wuln, Wx, where lane denotes the layer normalization operation. The gradients for this setup take the form nabla WL, W, equals NXK equals 1x, PW, Y equals K, X, P, Y equals K, X, I, WX, WX, caret T, WX, squared, Wu, K, X caret T. In conclusion, this section highlights the importance of matrix factorization and layer normalization in transformer architectures, emphasizing their roles in enhancing the stability and efficiency of these models. The proposed factorization method allows for achieving associative memory with reduced dimensions, while layer normalization helps in improving the training process. Layer normalization in associative memory models is examined, revealing its dual role in weighting updates based on prediction error and projecting them onto the orthogonal direction of Wx. This mechanism prevents excessive norm growth and encourages balanced weighting of frequent and infrequent tokens, becoming significant later in training as Wx is initially nearly orthogonal to any Wu, K. The authors also investigate the role of MLP blocks in encoding associations between input and output embeddings. They propose that MLP blocks can filter out noise arising from near orthogonality, potentially leading to additional storage capacity at the cost of increased computation. MLP layers are further highlighted for their ability to encode many-to-many associations, useful when considering multiple embeddings in the residual stream. This is achieved by defining embeddings UI as a weighted sum of individual embeddings, enabling the encoding of complex associations. The author's view of weights as associative memories is extended to multiple heads and layers, although they acknowledge the increased difficulty in identifying which layer or head learns certain associations due to redundancy. To address this challenge, they suggest the need for causal identification techniques, such as mediation analysis. Experimental details are provided, including the computing setup and hyperparameters used in each figure. Specifically, the momentum parameter is fixed at 0.9, and the weight decay parameter is set to 10⁻⁴. The uniform distribution over n is used for certain experiments. The authors present results from memory recall probes, exploring the impact of trigger selection and conditioning on the learning process. Figures 5 and 6 display the evolution of memory probes for various settings, examining the effects of different trigger selection strategies on memory recall. The results show that associative memories for the induction head learn slower when using few triggers, small k, rare fixed triggers, or random triggers. Notably, the probe for W2 with fixed triggers only shows recall accuracy on the set of triggers Q, a relatively easier task. Figure 6 presents similar results, but with the trigger distribution conditioned on the input data. The authors observe that memory recall probes exhibit different behaviors depending on the trigger selection strategy and conditioning. The experimental settings used to generate these results include varying trigger selection strategies, such as random triggers, π_q equals π_u, and different values of k, π_o, and eta. For instance, Figure 2 uses k equals 3, π_q equals π_u, and q is the k most likely elements of π_u, while Figure 3 uses k equals 5, π_q equals π_u, and π_o equals u. Figure 4, left and center, uses π_o equals u, d equals 128, and eta equals 1, with varying trigger selection strategies. Additionally, the authors visualize the weights W1k, W2k, and W20 after training with random triggers, k equals 3, π_q equals π_u, and π_o equals u. This visualization illustrates the learned patterns in the weight matrices, with each weight matrix W represented as W equals PIVIUI, where UI and V are the corresponding embeddings. These results and visualizations provide insights into the role of trigger selection and conditioning in shaping the learning process and memory recall capabilities of the model. When examining the performance of W2, a crucial aspect to consider is the interplay between dimension and learning rate on recall accuracy. Notably, increasing dimensionality accelerates learning, particularly when paired with a tuned learning rate. This phenomenon is evident in the recall accuracy curves, where higher dimensions yield faster learning rates. A key takeaway from this analysis is the significance of dimension in maintaining near orthogonality, a critical condition for effectively storing input-output pairs. This highlights the importance of dimensionality in shaping the optimization problem, making it better conditioned and more amenable to learning. Furthermore, visualizations of associative memory behaviors reveal that diagonal elements dominate, corresponding to correct associations. However, variations emerge when considering trigger token frequencies, indicating a nuanced relationship between these factors. By elucidating the complex interplay between dimension, learning rate, and recall accuracy, this research underscores the importance of carefully calibrating these parameters to optimize W2's performance. This refined text maintains the technical accuracy and depth of the original content, condensing the information into a concise and clear narrative suitable for voiceover narration. The training results of a more realistic architecture, featuring a ReLU MLP for the second feedforward layer, demonstrate similar behavior to the simplified architecture in terms of loss, in-context accuracy, and memory recall probes, as seen in Figure 10. Figure 11 illustrates the attention maps for a two-layer model with 4 attention heads, highlighting the challenges of interpretability in redundant models. The one-step model, defined by equation 1, successfully extracts relevant signal from noisy average attention after processing tens of thousands of tokens, becoming easier with increased dimensionality. This model's ability to identify memory associations despite additional redundancies underscores the need for further analysis to disentangle the contributions of different layers and heads.